Let's finish up chapter 21. So the next topic is find a force between two wires carrying a current. So for this one, you can go straight to this equation here. It tells you the force between two wires. You have two currents. You've got D, the distance between the two wires, and L is the length of one of the wires, the wire on which it's asking you to find that force. Oh, I do remember I did forget to mention in the previous video that when you are finding that force, you're using these two for the force on the charge or on the current. Sorry, I forgot to mention that. So back to this one here. So you want to know why there's a force on each wire. So the best way to look at it, I have two wires here. So we know this wire is producing a field. We know that the field is going into the page to the right of it and out of the page to the left of that red wire. Doesn't matter how far you are to the left, it's still going out of the page. I'm using that first right hand rule with the fingers curling in the direction of the field. The thumb was the current. So now we can just look at the blue wire. The blue wire finds itself in an external field here produced by the red wire. So then we use a third rule that says the current is up, the fingers fold out of the page, right, the field is out of the page, and that's going to put your thumb to the right. And that means that it will experience a force to the right. You can use the same method and you'll find that this one will have a force to the left. So this means that if the currents are in the same direction, the wires will attract. You can do the same thing with the currents in the opposite direction, and you'll find that the wires will repel. Now, instead of using this equation right here to find a force between the two wires, you could use this first equation here to find the field that we drew in red here, right? Because you can find this field at any location, distance r from that red wire. Then once you find this field, then you can go and look at the blue wire and say, okay, well, this is the external field here that I'm going to plug right here, and this is the blue current here that finds itself in this external red field, and I can get this force on this blue wire. But using these two equations will produce the same result as just using this one equation. And then the last topic in here is the torque on a current carrying loop. So we already discussed which way the magnetic moment is going to go. Now the magnetic moment is given by this equation right here. So the number of loops, the current, and the area of the loop. And so in this case, we said if the current is going counterclockwise, then the thumb points out of the page. That means the magnetic moment is going out of the page. And we want to know if you have this loop, and you have this loop, you can write here, in an external field, B field, is this loop going to rotate? So it depends which way the field is going. So if the field, this external field, was already going out of the page, I'm not going to draw the dots everywhere, but the field is already going out of the page, mu is going out of the page, then this B and this mu are already aligned, so there's not going to be any torque. But let's say that the field was going to the left. Then, so let's draw left here. We're looking at the field going to the left, not out of the page. It's going everywhere to the left. Now mu and B are not aligned. Your thumb, mu, is pointing toward you, and you can rotate that thumb to make it point to the left. So that means there will be a rotation of this loop. The best way to describe it in this case would say that this part of the loop here, this right part of the loop, is coming up and out of the page, and this part of the loop is going into the page. And that's the rotation. It's like there's an axis here, and you've got a rotation around this axis here. That's the rotation. So you couldn't really describe that as clockwise or counterclockwise. That one would just be, okay, well, this side's coming out of the page of the loop, this side of the loop is going into the page. So that this mu is now, well, the loop is now like this, it's now vertical, and mu is now pointing this way in the same direction as that external field. So that's the rotation. So if you start with the loop like this, so in this case what I was trying to draw, let's say that the current is going here in the front and this way in the back. So this is a horizontal loop. And so this would mean that the magnetic moment is going up. So now let's say that the magnetic field was going to the right. This is an external field here. Well, mu would want to rotate. So mu would want to go to the right. So that means in this case, you could say, okay, well, the rotation would be clockwise. It's going to rotate to the right. So there's not going to be any torque if the field is perpendicular to the plane of the loop, which means angle is 0. Remember that the equation that we're looking at is torque is mu b sine theta. The angle is between mu and b. So you can see in this case right here that the angle between mu and b is 0. This loop is not going to rotate, right? It already rotated from this position. So this is what this is saying. There's no torque if the angle is 0. And we're also saying, well, if the angle between mu and b is 0, then this means that the field is perpendicular to the plane of the loop, right? Because the plane of the loop is vertical, the field is perpendicular to the plane. That's no torque there. But really, it's very hard to try to memorize, is the angle 0 or 90? The best way is to just look at it and say, okay, which way is mu? Is mu already in the same direction as b? If not, then it will rotate. If it's already in the same direction as b, then there will not be any torque.